Hi guys, welcome into this video, and today I will talk you about drivers. So as you may know, most of the time you're just gonna take an IC driver for power electronics, which is basically a block in which you connect your MOSFET and put just a gate resistor here. And most of the time you don't even worry about what's inside in this driver here. Some drivers have also the possibility to have a feedback here, a feedback pin, a VDD, which is the logic connection, and most of the time also pin for the for connecting your MOSFET. But have you ever wondered what's inside this? So a driver is basically composed like this. You have first the pulse coming from the microcontroller or whatever it is. Then you have a level shifter, which turns this pulse here, which is generally speaking from 0 to 3.3 volt, to the pulse of 0, for instance 15 volts, 10 volts, something of the sort. So first of all you need to shift this square wave, and second you need to give the MOSFET a reasonably high current, otherwise it won't turn on. And so you need a amplifier, a current amplifier. And then there is your MOSFET with the net that you choose to design, so an RNG with diode, also with turn-off diode, whatever you need. So let's simulate this on LTSpice, and if the simulation is successful, I will also implement a boost converter. So let's open LTSpice and let's start with the pulse. So this is my pulse. Remember to define .param d equal to 0.5 and .param switching frequency of 100 kHz. So let's define my pulse as d over fs and 1 over fs. We can put the rest time to 10 nano, which is reasonably high enough, and V on 3.3 volts. So now we need to design a level shifter. Level shifters are basically a BJT transistor with a pull-up here, or even so this is the inverting level shifter. You can even use the common gate solution, which is done basically like this. You inject the signal here, and you have 15 volts here, and you have 5 volts here. So this is 5 volts, and at the end you are gonna have 15 volts. The common gate solution, the non-inverting solution, it is the most adopted, the solution here, and maybe I will try to use it later. For now, let's use the inverting solution, which requires just one power supplies, and it is the fastest and the easiest way to simulate an LTSpice. By the way, this circuit here is faster, dynamically speaking, with respect to this, just because of the parasitic capacitance that the signal is gonna see. So you're gonna see this parasitic capacitance here, but here instead you have just this parasitic capacitance, which does not affect so much the dynamics. So let's put the MPN with 1 kilo ohm resistor, and let's just put the 2N2222, and let's use another voltage which we called logic voltage. This is the logic voltage which we supply our logic driver, and let's put it to 10 volt. and this has nothing to do with the input voltage of our DC-DC converter. So now at the output of this, you would expect the same input but inverted. And as you can see, we designed successfully a level shifter. But as you can see, there is a little bit of delay, which is not so good because it's gonna hit some duty cycle. For this reason, you can use some acceleration techniques. The first that I can think of is just to put a capacitor here of 500 pico, or even a Schottky diode between the base and the emitter. That should accelerate a bit, and in fact it did. So we are trying to bypass this resistor by making the dynamic faster, and as you can see, the delay has disappeared. Yes, there are some spikes. As you can see, there are some spikes in the turn off here, which are not so good, so we need to clamp this turn off. Okay, because this minus 3 volt can destroy our MOSFET, so even before putting the amplifier, I will put another NPN transistor. I will put another PNP transistor, which basically tries to clamp which basically clamps the turn-off region. So let me just put this transistor here, and let me put also a Schottky diode in the turn-off path, so that we will have a clamping and avoid this minus 3 volt, which is not so good, by the way. So let me put a very fast diode, the Schottky diode. Let me put it here, and let's analyze now the voltage here. We are making the turn off faster, but in order to that spike should be gone in the MOSFET with this solution. I don't know why you can see just here. It is very strange, by the way. There should be. Okay, I don't know what to say. These spikes here should not be present. Okay, let's go on. By the way, so let me put now the amplifier. Okay, so now we arrived there. We need the current amplifier. For the current amplifier, I will choose the push-pull configuration, which is basically made like this. So you have first the PNP here, and second the NPN here. So basically you have enhancing the current, and that will give a very high output current. So now you have just to place the MOSFET, and the simulation will be over. So let me put an NPN here. The same NPN, by the way. And let's put a PNP Let's put a PNP here. And let's ground this. Now let me connect properly the MOSFET. We should have also the input voltage, and this will be our input voltage of 50 volts of the boost converter, for instance. So let me put also the capacitor, because boost converter will have the input capacitor, the micro, let me just put just the MOSFET for now. Okay, and then I will realize in everything is working, I will realize a boost converter. Let me put just 5 ohm of gate resistor and a MOSFET of this with a load of 1 ohm. And let me run the simulation. So we have the pulse. Let me call this node G. And let me analyze the input voltage and the G voltage. So as you can see, we have the G voltage, the gate voltage, inverted with respect to the input voltage, and of course we have also cut the negative side by making our level shifter well designed. Now if I cut this part, so let me just connect this to this and run again. As you can see, there is a constant voltage in the turn off, which is around the VCE of your BGT stage, which is more or less 0.7. So in order to avoid this non-zero voltage in the turn off, you have to connect also this. And if you don't place this capacitor here, this acceleration capacitance here, as you saw in the beginning, there's gonna be a delay. So as you can see, let me stop for a moment. There is a consistent delay between the input pulse and the final pulse, which is something that you don't want. Okay, so now we can say that the gate driver is complete. Let me tune for a bit. Let me tune for a bit the gate resistor. So as you can see, we have a little bit of spike here, and the gate resistor is needed, but maybe it's attenuating a little much. So let me put just 2 ohm, and let's see what happens if I put the this is the contrary, by the way. So that we are enhancing both turn on and turn off. Okay, so now we have realized a very, very fast turn on and turn off gate, as you can see. It is also very well attenuated, so there are any kind of spikes, which is good. And there is a minimum bit, the delay has been minimized, which is also good. Now what we have to do is to use these loss drivers to, for instance, design a boost. So now we can really design a boost converter by placing the input capacitor here, input inductor, sorry, of, let me put 47 micro, because this is a very high voltage. And let me put also, by the way, the boost converter has the input inductance, the low side switch, and the high side diode here, connected with the load, the capacitor and the load. So let's connect the diode, the Schottky diode, and let me connect here output capacitor of 10 micro, maybe a little higher, and let's put also some banks of output capacitor, because you want to reduce the ESR, which will be still present, like for instance 10 milliohms. So let me put a bank of output capacitances, and let me put the load of 1 ohm. So let me draw for a moment because it is becoming very big. So all of this is the driver. Uh, and this is the boost converter. Just this? Yes, because you can make a boost converter with just 3 components, if you think. So this is the low side driver and this is the boost converter. Now, hypothetically speaking, this is just the open loop version, so as you may have seen in other videos, you need to close the loop with a comparator, with a compensator, everything that you need that will generate the duty cycle needed based on the reference. Maybe I will do it later, but for now let me run the simulation and let's see what is going on. So first of all, let's analyze the gate driver. The gate driver has not been modified, hopefully. So now let me see the inductor current. The inductor current as a transient, but after that it is just in working CCM condition, which is not good for the boost, because boost always work in DCM apart from PFCs. And now we have the output volt. Whoa! What is this? Should not be so low, by the way. Ah, yes, because I am inserting the ESR. ESR affects greatly the output voltage. If I cancel this ESR, you're gonna see a way smoother output voltage. Yes, that should be true. Yes. Since the duty cycle is 0.5, we almost expect the output voltage to be double the input voltage. So this is reasonable. This is really a reasonable output. Now let me put also, for completeness, if I can find it in few seconds, let me put for completeness the let me put for completeness just the yes, just the output, the control here, which I did in some other videos. Let me cancel the integral part because I do not have the time to tune it. Let me put the reference to 90 volts and let me close the loop. If it is working, it's at the first try, it is fine. If it isn't, I will do another video in which I will make a completely. So let me cut these parts here and let me put the output of the triangular waveform here. Now the loop is closed, even though you can't see because there are the labels, but the loop is closed because basically what I added is I added a network of just a PI controller, and this is the comparator and this is the triangular waveform. So here there is the triangular waveform compared with the comparator, which goes inside the comparator, and this will generate the square waveform that I gave at the beginning of the video. So if I run again the simulation, and if I did everything correctly, it should work. Duplicate definition of FS in the ET, he is right. Okay, so this guy has saturated. Let me think. This was a previous bug, by the way. Okay, so I will make another video to close the loop, because I don't have. Okay, let me turn to the open loop configuration, because I think that this is enough for today. So let me analyze also the other waveform. This is the waveform of the current of the diode. This is the waveform of the current of the MOSFET, which is MOSFET plus diode. As you can see, composes the inductor current as we expect. So I will make another video which I will close also the loop with a type 2 compensator. So from now on I will use this low side driver here, and since we want also to make the hierarchical component, we can, theoretically speaking, open a new schematic and just put all of this into another draft, and we can call it, we can just make here pulse, sorry, not pulse, but as an input we can make VDD. This we can cancel it, we can cancel this, we can put our label called input, call it pulse, and we can make the last label which calls we can call it as out. We can create the symbol. We can call this file save as low side driver. We can call it in this way. Now we can go to hierarchy and create a new open this sheet symbol. It will generate one directly, and as you can see, it has generated our low side driver. So now if we go back to this and we cancel all of this, we can just go to auto-generated circuits, and we should find our I don't know why I can't find it. Okay, low side driver. I found it now, and let me connect the pulse here. Let me connect the logic voltage to VDD, and let me connect the output voltage right there. Now, if everything has gone smoothly, I should run the simulation, obtain the same thing as before. Exactly like that. So once you have confirmed your solution, you can also make your integrated circuit like here, to occupy less space as possible in the circuit. Otherwise it will be impossible, basically impossible to read. So this is the final solution. I can think that we can close the video here, since we'll be quite long. Thank you for your attention. Thank you for your attention, guys. Thank you for watching this video, and see you in the next one. Reply in the comments if you want some videos about power electronics, and I will try to make on LTSpice. Bye bye.